Hello, everyone.
Hello, everyone.
Once again, it is a pleasure to welcome you to our studio, 1C Game Studios. Today, we are going to record another wonderful episode about jet engines. And with us in the studio today is the person on our team best able to provide information on this topic, Alexander Mironov. Hi, Sasha. Okay, well, let's probably start by introducing you a little bit. Or you can introduce yourself. What is your specialty? How did you come to us? And how long ago? All of that.
Hello again. My name is Alexander. I am an engineer in our team. I work on flight models, damage models of airplanes, their systems, autopilots, and so on and so forth. I have been on the team since the very beginning, you could say, when we got together in 2012, I think. Yes,
that's the year.
I got involved with the team through an ad posted by our then lead engineer, Andrei Petrovich, on the well-known forum known as Avsim, where I saw the job posted.
Yes, that forum is still around.
I haven't been there for a long time now. But yes, I answered the ad, went through a multi-step interview process, and ended up here.
Who were you, and who have you become in that time?
Well, basically, I came for the position of flight model and damage model engineer and all that. And so I worked as an engineer.
No, well, you started out as an engineer making flight models, so you were making aircraft after aircraft and doing research for each one. But now you are working on broader tasks.
Well, if you look at it that way, yes, there is a progression from more specific tasks to global tasks, such as jet engines.
Yes, and in Korea, you were assigned to the jet engine project. How did it happen that we suddenly had to change something about the engines in Korea? It seemed that we already had it. We had two jets in the great battles, the Messerschmitt 262 and the Arado 234. Both had the same engines, if you remember. Why did that model suddenly become inadequate, and what needed to be improved, changed, enhanced, or developed?
Well, it turns out that there was only one engine, even though there were two planes. So I think the Yonkers Jumo 004B in particular had very good reference data. Thrust data, well, fuel consumption is not that critical, but thrust over the full range of altitudes and speeds is what we needed in the game. Based on that data, the engine was, you could say, already there. This data just needed to be used at the right time. And so we had a problem where these secondary engine characteristics, like airflow and fuel consumption, they had to be calculated backward. That is, we had the fuel consumption, but the airflow was calculated based on the available thrust. So the calculations were all done in reverse. And when we build a new airplane with a new engine, we have to find the same reference data all over again. And we need to do a reverse calculation again to get those specific characteristics. This would have to be done for every plane, all 5 engines. So we decided it would be better to go the normal route, as they say. And how do we calculate this? In the real world, all of these input parameters...
In life, I mean somewhere, in a design bureau.
Or when analyzing the characteristics of engines, yes. Basically, when you're designing an engine, it's pretty easy to make a rough estimate of how much thrust it's going to produce and how much fuel it's going to consume. In general, a jet engine is one of the simplest engines if you look at it as a whole, without going into details. These parameters are calculated sequentially from the engine's intake, the intake system, the compressor, the combustion chamber, there are usually several, the turbine, which can also have a couple, to the nozzle. The afterburner chamber may be located in front of the nozzle. By sequentially calculating the engine parameters, such as airflow, pressure, and temperature, you can calculate these parameters over each engine section, with their own parameters. And in this way, looking ahead, we can implement a damage model. By damaging individual components, we will directly affect the performance characteristics of the engine.
So, roughly speaking, there is a kind of chain from input to output, where you can introduce some disturbances in the form of damage in the middle that will ultimately affect the overall characteristic.
Yes, it affects the thrust. At the end of the day, we have to get a certain amount of thrust to move the airplane forward. In the old system, in the old engine, it wasn't so easy to change something and get a result, to be honest. You had to think of something.
And in the old system, it was like a
In simple
monoblock.
terms, yes, it was a monoblock that provided thrust depending on the position of the lever, and on the atmospheric conditions, of course. So, and here we come to something in the engine that, again, in reality, when the engine is designed, is called the compressor characteristic. This is one of the most important characteristics of the engine. It is either obtained from real tests, and any change in parameters, even geometric changes in the compressor, requires retesting. Now, with the development of computer technology, computational fluid dynamics can greatly simplify this task. However, the problem is compressor characteristics for jet engines are not easy to locate. So, instead of us searching, and perhaps because they were never published for these sorts of engines, it was decided to go by reference, using the already calculated characteristics of the engine thrust and flow rates to build a semblance of this map. It is called a compressor map in English engineering terminology, actually. So the task involved constructing kind of a semblance of that characteristic, interpolating it into the necessary ranges, and then, based on this resulting data, correctly modeling a new engine.
Well, as always in the development of flight simulators in all sorts of directions, it always goes from some general basic solutions to greater detail to more complexity of the model and the composition of its components. So when Roman and I talked about aerodynamics last time, well, actually, the same story was quite similar. Yes, that is, we will now consider a greater number of aircraft components in aerodynamics. Well, not only in aerodynamics, but in physics in general. For example, when calculating the strength of the aircraft and its structural integrity, more elements will be included, like spars and all that stuff that wasn't there before. Some statistical models were applied in those places in the previous project, speaking of great battles. It's a similar increase in fidelity here. Could you highlight some features in the new engine model that, let's say, a player of Korea might like and be interested in?
All right. Well, I think the main characteristic of a jet engine, so to speak, is its, let's just say, it is an abnormal operation known as compressor surge. It's a well-known phenomenon.
Everyone knows the term, but not everyone knows
All
what
right.
it means.
So compressor surge is what in engineering is called a disruptive phenomenon, a disturbance in the normal flow of air through the engine duct, even causing the air to flow backward, because a higher pressure is created behind the compressor than in front of it, reversing the turbulent flow. It doesn't flow forward as it should normally, but is pushed backward by the pressure, which then balances out. The compressor builds up pressure again in that direction, and it gets pushed out again, characterized by a sound like puff, puff, puff. Everyone has heard it when watching the videos of how it
By the
happens.
way, it's funny that this is actually a visual effect of surging. Most of the time, what we've all seen on the internet, in YouTube videos, on airliners, the flame is usually thrown out, and the engine works intermittently like this. Puff, puff, puff. And that makes noise, as they say. But sometimes the flame is thrown in the reverse direction, towards the aircraft nose.
Towards the
Yes.
nose, yes. So if we had a simplified approach to compressor surge modeling before in great battles, now we can vary its occurrence. We can now vary it depending on angles of attack, airflows, and damage to engine parts, things like that. We can make it visually, either an exhaust at the back of the engine, flames, burning smoke, or the front exhaust, or in the worst conditions, when conditions converge. The engine will not exactly explode, of course, but something like an explosion will happen, and it will just stop working properly, just turn into a pile of metal. All these phenomena can already be realized in the new model.
So it's not just a surge anymore. It's a whole range, a kind of spectrum of variations of that effect.
Well, the simple part is that if there are individual engine components, each of them can be damaged separately and will have some impact on the engine's characteristics. Or, on the contrary,
Any of them
they may
can
have
be
no effect at all,
damaged.
and it
For
will just continue
example,
working.
I could hit the turbine, knock out a couple of blades, and as a result, its efficiency will go down, and the compressor speed will go down.
Yes, the thrust will disappear, well, it will drop, and the RPMs will drop. By the way, there was a case where a blade was lost somewhere in the middle of the compressor, and it flew out, so fortunately, it didn't cause any damage. The blade was simply found in the nozzle assembly during a pre-flight inspection.
And what type of airplane was that?
I don't remember. I will check and let you know. Okay.
Let's tell. Curious how? No vibrations? None at
No
all?
one felt any vibrations. Only an inspection possibly prevented an accident of some
Wow,
sort.
look at that. All right, one more question for you. All 5 jet engines that we will have in the Korea project, all 5 of them do not have annular combustion chambers like modern ones, right? They have tubular chambers. Yes, separate pipes. Each combustion chamber is like a separate tube. Will it be possible to knock them out one by one?
Yes. If we make a separate collision model for each chamber, we can definitely knock them out individually. For example, you could sever the fuel line, and the fuel would just leak out. Then it could catch fire, and consequently, the engine will just burn.
Let's go ahead and let's look at the question of what jet engines we will have in the Korea project. We are planning 5 jets. We've already announced almost all of them, but today it seems we will have to give the full list. Let's start with maybe. Let's save the MiG-15 for last, since it's the only Soviet jet in the simulator. Let's start with the American ones and work our way up from the simpler engines to the more advanced ones. So let's start with the F-80. What kind of engine does it have? This is the F-80 Shooting Star. What are the characteristics of its engine?
So the F-80 has the General Electric J33 engine, sometimes called the Allison J33. Well, the company that developed and then manufactured it, it's understandable.
At some point, somebody bought somebody out or something like that.
I don't know. There were some complications.
At some point, somebody bought somebody out or something like that.
In fact, for those of our viewers who are not aware, jet engines are basically classified by compressor type into those with centrifugal compressors and those with axial compressors. An axial compressor, if you've seen pictures, is a shaft with a large number of wheels with blades. Each of these bladed wheels is a stage. There are 11 or 12 stages. I think we have exactly 11.
Well, it's the classic type that you can see at an airport. If you look at the jet engine of a passenger plane, it has an axial compressor.
Yes, but what you see at an airport when you look directly at the engine is called the fan. And it is sort of an extension of our engines that we have. It's, well, an even more complex compressor that we don't see at the core. So, a centrifugal compressor is a simple impeller. I don't know who's seen it. For instance, you can find a centrifugal compressor in a car that has been fitted with a turbocharger to its engine.
Well, maybe you've seen it and you know what it looks like. It's like those large old industrial fans where there's a big snail shape and inside there are blades that accelerate the air to the edges of the housing, creating pressure along the edges, and then it goes on under pressure.
And so, with the centrifugal compressor, the English were the first to make a couple of engines, known as the Nene and the Derwent, I think. And based on the Nene, many engines were made, including Soviet ones, by the way, but that's later. And the General Electric J33 is also basically a development of this English Nene engine. It has a centrifugal compressor, and it's designed with 2 intakes. So these wheels with blades, there are 2 of them, and they're connected like this, with air coming in from both sides and going out through the perimeter.
So, basically, I don't even know how to explain this, but let's say the engine, right? It has the compressor here, the air comes in from here, and like that, right?
Yes, it comes in from this side, and there are meshes so that nothing bad can get in, and there's a mesh on the other side too. Air goes into these. They don't communicate with each other, these 2 rings, only at the end when the air goes into a diffuser and then it enters the combustion chamber. Because the compressor is such a large wheel, The combustion chambers have to be spaced out higher, making these engines very wide in diameter, but they can also be shorter in length.
By the way, if you look at a jet engine without its cowling, it's very easy to tell the difference between an axial compressor jet engine and a centrifugal compressor jet engine. If you just see a long tube, it's an axial compressor engine. If you see something more barrel-shaped that isn't very long, then it's most likely a centrifugal compressor engine.
And these combustion chambers, which are angled away from the engine axis and tilted from a larger diameter to a smaller diameter, are barrel-shaped and have a variable diameter. They transition into the turbine. All of our engines have one turbine. Let's not get bogged down in discussing details that it could be two, with two more oval shapes.
All of
But
our
ours
engines are
practically
single-stage
single-shaft.
turbines, right? Yes, they are. That means they have
And
one
our engines
shaft
don't have
and one rotor.
afterburners yet. Well, in the literal sense of an afterburner. But if it's not literal, it's quite surprising. I just know, when I decided to look at the Sabre, maybe there's some feature. Well, Wikipedia as a source is not great, of course, but it says that there's additional fuel injected into the combustion chamber, but it's a little behind. We also heat the gases, which then spin the turbine, and as a result, of course, with increased fuel consumption, we get additional
Well, it's not
power.
exactly afterburning. Afterburning is when you're all the way at the tail after the turbine and you're injecting fuel. But it's
Well,
close.
for some reason, it was called afterburner.
So it's basically just an extra injection of fuel before the turbine, which is essentially afterburning. What's so special about afterburning in a jet engine? When you're in the afterburning chamber, you have a compressor, a combustion chamber, a turbine, and at the end of all that is an afterburner. If you inject fuel into the afterburner, it doesn't affect the torque on the compressor. It just increases the final thrust. It doesn't make the turbine spin any faster. But here it's kind of,
Well, we will have to look into this in the future, and if necessary, we can implement the
By the
so-called
way,
afterburner
about
there.
the strange terminology in the sources. For example, when talking about the F-84 aircraft, VIX recently was going through documentation. Vitya Sechnoi was with us here, and in the 1950s, all the official documents called it a low wing, although its wing clearly goes through the center of the fuselage. Everywhere it is called a low wing, but from the 1960s, they changed it to a middle wing. I guess they decided to rethink it.
Let's continue. We also have the centrifugal compressor in the Pratt & Whitney J42. Interestingly, the Americans named all their engines with a J, probably for jet.
Well, jet, probably,
But
yes.
it's the Pratt & Whitney J42. It's on the Panther F9F.
Prolific jet engine, yes?
Yes, it is probably the most widely used jet engine when all variants are considered.
Was there anything different about it, or was it all the same?
Wait, are you talking about the engine? The engine is exactly the same.
So it has a different name, but structurally, it's basically the same, right?
Yes.
It also has those two compressors, right?
Yes, the most interesting thing is that it was also a development of this Nene. It was just built by a
So
different
they
company.
all went to Rolls-Royce and got a license from them. Yes, they did. In short, Rolls-Royce probably benefited the most.
The
Can
most
you
interesting
imagine how
thing
much
is
they
that
earned
when
on
General
that license?
Electric moved to axial compressors, after they made the 33 for the F-80, they saw they had a lot of time and thought, why not make an axial compressor? And so they developed the J35 in parallel with the F-84. In principle, they could have tried installing the J33 on prototypes, but then they saw they had the J35, which was good, so they decided to install it.
That's fascinating. Now, what I find interesting is that if you take a close look at the F-84 itself, it ended up with a more noble, elongated profile. I guess that all aircraft fitted with centrifugal compressor jet engines are a little more barrel-shaped, so to say.
That diameter had
You
to
can
fit
clearly
somewhere.
see that they are squeezed in, while those with axial compressors are more elegant and cigar-shaped. So let's discuss the axial
And
ones.
so the 35 became the 47. Well, not directly, but as an evolution of the J35, the J47 was built, which was installed in our most mass-produced Sabre, the F-86.
I see. So it really does look like the same engine, right? I mean,
Yes, yes, yes.
J35 and J47?
But what I mean
Interesting.
is the Sabre, the early versions, the A series. Because in the later series, the 73 seems to have come in. We're not thinking about that, not at the moment. But the development is basically going in one direction. Increasing performance, decreasing weight, decreasing cost, and so on.
Yes, yes, I got it. So, continuing the discussion, how would you say this issue was organized, generally speaking?
Now, if we are talking about the axial compressor, it has an elongated cylindrical engine, and I believe the compressor has a total of 11 stages with a pressure increase ratio of up to 5 if I'm not mistaken. Oh, and it should be noted there were also a total of 8 combustion chambers.
They are
And
arranged in
altogether,
parallel,
there
like
were
in a
8
revolver.
such pipes. Concentrically, yes, just like that. And also the turbine. The typical turbine, yes. It's just one stage, it's all on one shaft, non-multi-shaft engines. And by the way, on all our engines, at the exhaust, there's no cross-section regulation, no regulation at all. Interestingly, the German engines had a movable cone. German engines, I mean the Jumo.
In the back, right?
Yes, it was in the back. That cone could adjust the parameters slightly, depending on the mode. But there is no adjustment here.
By the way, I hadn't thought about that because, well, I thought it was normal. For a jet engine without an afterburner, the absence of an exhaust nozzle adjustment is generally quite normal. If you look at it, at least all civil aviation doesn't require it. Well, in general, yes, it's not dangerous.
This is when we can pump so much fuel into it that all we have to do is add air, and the air has nowhere to go. So we definitely have to do something about it.
The problem there is, when your engine is on afterburner, you have to change the nozzle profile, change the longitudinal section of the nozzle from a regular one for a non-afterburning engine, which in such a profile simply narrows down to a Laval nozzle.
Yes,
supersonic. Yes,
First,
a
it
supersonic
narrows,
Laval
and
nozzle.
then the gas velocity increases. At the critical point, it becomes supersonic. Then, to increase the velocity further, we have to widen the nozzle.
This, by the way, is great magic that's very hard to understand. You have to watch YouTube. There are a lot of videos on YouTube about nozzles. Watch them. It's really fascinating how when the nozzle expands, although it may seem that with supersonic gas flow, the gas flow velocity increases. In fact, if you have an afterburner engine, when the afterburner is turned off, you have subsonic gas flow. If you need to create a supersonic jet, when you pump in the afterburner chamber, it allows you to create a supersonic jet precisely. At the engine exhaust, you usually need to convert a converging nozzle into this type, and that's why an adjustable nozzle is characteristic of engines with afterburners. But that's not the case here, and why it was needed on the Jumo, by the way, is not very clear.
Some of the early engines were made in a way that the speed needed to be more finely tuned. Maybe they had instability in certain modes. Finicky, yes.
And with our engines, aren't they just as finicky to operate as the German Jumos?
By the way, no. Another major problem with the Jumo was that, unlike piston engines, jet engines are very, let's say, lazy. I forgot what the word is. Throttle response, yes, that's the right word. They have very poor throttle response in comparison to piston engines. That is, the time it takes for the engine to go from low throttle to nominal throttle is very long compared to a piston engine. And during that transition to those revolutions, you cannot immediately open the throttle and wait to see what happens when there are no fuel control systems fitted. That would just flood the engine with fuel and cause an engine fire. And to prevent a fire, they didn't immediately put a responsiveness valve on the Jumo to prevent these fires.
I think we made a modification for this.
Yes, we have it as a modification. It's there specifically to make it more interesting for players to fly without it. But all the post-war engines already had those nuances built in to prevent accidental engine burnouts. Those valves were installed, and there was fuel automation to ensure a proper transition process.
It's amazing that all of this fuel automation involved absolutely no electronics.
Yes, purely mechanical.
Purely mechanical governors, meaning that there are pressure ports in different parts of the engine that move the control valves in a certain way. When you try to understand that, it's really unclear how you could even come up with that idea, to be honest. Well, we still have the main star here, the MiG-15.
Here is the MiG-15, which surprisingly or not so surprisingly, was also based on the Rolls-Royce Nene. Rolls-Royce was really involved. Yes, many probably know the fable about how allegedly Mikoyan won the engines at billiards. These Nene engines were officially bought from the English by the Soviet Union. Its Soviet copy was called the RD-45. Then, according to the technical specifications, modifications were made, the engine was made a little bigger, and accordingly, the thrust was increased, and some Soviet production technologies were applied. It was called the VK-1, and indeed, it became one of the most widely produced jet engines. It is still used today in airport vehicles, yes, to blow snow and clear ice from runways.
Well, you have to understand that copying an engine is still a ton of work, because it seems like you have everything, all the documentation is in your hands, and there are even samples, so just finish it. But no, you actually have to build an entire technological chain. You need to fully understand how it works, to grasp all of the underlying theory, because without that understanding, you won't be able to assess or address any deviations that might occur in the engine's operation. So it shouldn't be a black box for you, so that you can somehow implement and develop this further. And all the technological processes, because a jet engine is obviously a highly stressed machine that operates at extreme temperatures. Blades, these turbine blades, require special materials. You need to know materials science just for turbine blades.
These alloys should be hard and heat resistant. The industry boomed after the war, not only because the new engines needed to be produced, but also because the B-29 bomber was advanced for that time. And so, all this boosted the industry significantly.
Yeah. So, there's a good example. If we take a tank, like an Abrams or a T-90, along with a complete set of design documents, and let's say we put it in a time machine and send it to the 15th century. It won't help our ancestors there, because even if they understand what's written, they won't be able to replicate it, because the production technology can't be replicated in those conditions. So they're going to have a tank that's just draining money and will bog down somewhere, because they wouldn't even be able to produce the fuel. Yes, even the fuel. It certainly won't run on firewood. Let's move on to the questions, shall we? Yes? We have some questions from you, dear friends. Be sure to ask your questions. For each upcoming session, we usually collect your questions beforehand. What concerns you about the next topic, the next meeting? This is the question we are asked. Have you done everything you planned for the engines, or are you still working on something? And what problems have you encountered?
So what I can say right now is that the work on the engines is not finished, and in fact, it will continue during the process of working on each aircraft. Simply put, there is a time allotted for this aircraft's engine, and during that time, its model will be improved. Currently, we have a model that generates thrust and operates over the full range of altitudes and speeds, but certain transition processes still need to be modeled. We are working on that right now, and so the damage model, the visual damage model, and some of the other features that we talked about today still need to be done. Work is in full swing. The main difficulties, or rather the main difficulty I would say, is finding a compromise, because this is such a broad topic that it's easy to get bogged down in it. One can work on this sort of thing a lot and end up with something, but end up with an incomplete solution. Because of that, it's better for us to start with a simpler solution and then refine it as we go along.
Yes, unfortunately, we've talked about it before, even discussed it with Roman. We had similar problems, for example, with the fuel system. So you can't say that someone did something wrong. The task was done right. The task was to make a complex fuel system. That was our focus. The person put in maximum effort, but the task of making everything as complex as possible was so hard that it wasn't feasible within reasonable game development timelines. Well, in other words, it turned out to be impossible to do it in about a year and a half. And what could one expect, roughly speaking, when it takes 10 man-years to develop a virtual aircraft, and here a complete megaphysical engine model, not just the fuel system, with all the hydraulics done? It doesn't work that way. People don't work that way. People sometimes work on such things for decades. Next question. Early jet engines, as the author of the question mentions, were very susceptible to effects like compressor stalls and all that, especially under certain unsteady flight conditions. Large angles of attack. I'm not sure what else it could be. Climbing high, pressure drops, different unsteady conditions.
Bird strike.
So, how will we represent all of this in the sim, since our jet engines are such early models?
Yes, an early engine. That's right. Any sort of jet engine can go into this mode, but to avoid this sort of issue, there are some modern engine design features that these early jet engines didn't have yet. Well, maybe just bleed valves. I think some have them. I think they are on the F-84. Those engines don't have any features to help avoid that type of condition. When these conditions are met, as I mentioned, we will regularly encounter this compressor surge based on the compressor's characteristics. There is a zone of unstable operating modes where we have a high pressure rise, but at the same time a low flow. Essentially, when we reach high angles of attack, we find ourselves in these conditions. We will regularly experience surges. Where there are bypass valves, these unstable modes will shift slightly. If there are no bypass valves, we'll catch the surge more often. We sustain damage from something. Here you go, a surge. Maybe even a flameout.
In the combustion chamber, right? So it just blows it out, right? Yes, and the fuel can be blown away and cause a fire further down the road.
Then everything will catch fire and the engine will burn out.
So we will have that presented. All right, I have a personal question. If you compare a machine with an axial compressor and one with a centrifugal compressor, which one of these is more prone to compressor instability? Which one is more temperamental? Centrifugal, yes. More fragile, right? More fragile. So axial is more stable in that sense. It is considered
like
that way?
Interesting.
Yes. All right, well, the last question for today's discussion. This person is asking about something in great battles. If there are any engine operating modes that are not allowed by the manual to be used for more than a certain amount of time, then you just have a timer mode after which.
Well,
we have it. We have it. He tells us that we have it, like we got it. Yeah, there's just a timer implemented. When it runs out, the likelihood of the engine failing kicks in. He asks if this is implemented differently in Korea in terms of afterburners. That is, how will limitations in the engine be handled, the afterburners limitations? Will they be implemented in the same way or somehow more interesting and realistic? First of all, we have to reply that we are not going to have engines with afterburners in the Korea project.
We won't have any engines with
During
afterburners.
the Korean War, there weren't any planes with turbocharged engines or jet engines with afterburners. Well, except for this odd case, something they call an afterburner in the F-86. But that's kind of...
There was the VK-1F engine with an afterburner.
Did planes with this type of engine reach Korea or not? They did not. Correct. Let's say it anyway. Maybe something will change in the operation of our piston engine damage logic in Korea or elsewhere in the future. Yes.
We still do have timers, but not in the way you might think, like exceeding the maximum speed by 1 revolution per minute and immediately triggering a countdown timer. No, we don't have that. What we do have now is the concept of event probability, and we arranged it so that after this limited time, the probability of the event increases as time goes on. And after some time, this probability reaches 100%. This means that the engine that is supposed to work in this mode only for a limited time will definitely break down at some point, but it won't break all at once. It just has increased friction in the crankshafts, so to speak. This causes the engine to start producing less power, possibly causing even more friction, with the potential for an avalanche-like event to occur, when the engine just freezes up and stops. But when you're already beyond that safety limit, you can simply reduce the throttle. And already, these potential problems, their probability may decrease. It certainly won't be as new as it was before the damage, but at least it will be able to help the pilot reach his base. Yes, there is such an idea of getting rid of the timer altogether, but for that, it is necessary to introduce some entity. Local overheating, something like that. To model it separately, it would be very fair to our players, because this thing can be implicit, not to show it like in the old IL-2 1946. When it overheated, they opened some kind of radiator, even on planes that didn't have one. And everything was fine. The engine didn't overheat. To avoid that, we have to make it implicit. But the players should be able to judge the state of the engine indirectly, by the RPM fluctuation and the temperature rise, and we can add something audible. This will add elements of variety and make it more interesting to play. But we're not going to change the fact that we have a new plane on every flight for now.
Well, yes,
that is
the
a fundamental design
stance
principle.
of this design.
Yes, it is. If we go further and maintain the condition of the engine from flight to flight, then this new system I'm talking about will really shine. You're going to preserve the engine between flights so that it lasts until the next flight. And for example, if you introduce an element of economy, yes, you can order to repair the engine, but it's going to cost you, let's say, how many days you're grounded, I don't know. Well,
I don't know, not being able to
There
fly.
are a lot of interesting things you can do. But again, that's a game design question.
Well, there's also this point. In each specific aircraft, the time limitation of the takeoff mode or the combat mode or the forced operation of the piston engine can be caused by completely different reasons. On one engine, the cylinder heads overheat, or there may be a problem with the compressor. If it has a turbocharger, something may be wrong, such as overheated oil in the turbocharger. The problem is that they didn't specify anywhere what causes these time restrictions. There's just no data, that's all. It's mentioned occasionally on one plane, and we have 100 of them, but not on the others. And now we have to make an informed guess as to why this is happening. Why exactly is there such a restriction on this particular engine, and based on that assumption, to put the appropriate module into the physical model of that engine so that something starts to heat up and break? That is the challenge of research. But we are moving forward. I think one day we will get there. Well, dear friends, thank you for being with us. I hope you enjoyed it. Personally, for me today, my specialty is hydraulics, not jet engines. Sasha can explain the engines to us much better than I can. So, Sasha, thank you very much for coming. See you back in the studio, and please subscribe to our channel, like our videos, and stay tuned for new releases. Bye, everybody. Bye-bye.